The first question that I received is regarding variable speed drives. Okay. Pretty open-ended question. It's a good idea to ask open-ended questions during your exam preparation. Okay. And I'm pretty sure you can Google this, chat GPT this, you can, look up a textbook or whatnot, and it will probably give you a pretty decent response. But it's not necessarily the answer that I want you to um, basically work towards necessarily as an end all be all type of stuff. It's a thought process, because once you get an understanding of or develop a framework, an effective framework of approaching these problems, you're going to be more confident and comfortable on the exam. And the P power exam, as we know, is not a plug and chug, right? Compare the sample exam from NCS for P power with the sample exam from NCS for FE electrical, and there's a day and night difference. Okay. So the question is, what are the pros and cons of a 12 pulse drive? Okay. Compared to a 6 pulse drive. It's pretty open-ended, right? So in your mind, first of all, I don't think a question can be asked, like it's not an essay style exam, so you cannot sort of list out multiple options. But I can think of ways in which such a question can be asked, like drag and drop, maybe match the columns, that which features, which characteristics apply to a 12 pulse drive, which characteristics apply to 6 pulse drive. So maybe in that sense, you can create questions where you can test more broadly on your understanding. Okay. So how would you guys approach it? So we are doing a comparison between 12 pulse and 6 pulse, right? Which one is better? Let's start with a very simple question. Which of the, if you give an option to choose between 12 pulse and 6 pulse, we all agree that 6 pulse drive will be better, correct? So we are starting with an overall qualitative assessment that a 12 pulse drive is better than a 6 pulse drive. Agreed? Now, when we start digging in a little bit deeper, why is a 12 pulse drive better? What is the difference? Maybe we can look at it from performance standpoint. Maybe we can look at it from the construction standpoint, i.e. the configuration standpoint. Okay. Maybe we can look at it from the standpoint of harmonics. Okay. So these are the different things that you should start exploring, right? Different directions you can start moving into, right? So give me a couple of reasons or examples why you think 12 pulse drive is a better option as compared to a 6 pulse drive. And again, the way that we approach these problems, I would recommend is start very broadly. Ask simpler questions, because when you ask simpler, broad questions, it will give you a certain direction and focus. And once you lay out, okay, broadly speaking, these are the different directions I need to sort of dig in further, then you can be more and more sophisticated. Does it make sense? Okay. So don't be thrown off balance by application oriented problems. Always bring them to first principles. Now, within the coursework, within the context of harmonics more precisely, we discuss 6 pulse converter and 12 pulse converter, right? The VFD actually has a front end, okay, where we take the AC input and convert it into DC, and that is basically a rectifier. So when we are talking about 12 pulse versus 6 pulse, is it in the AC to DC conversion phase, or is it in the DC to AC? Because ultimately the output from a VFD is what? AC, right? Variable speed drive. You have, you can argue that they're DC drives and whatnot, but strictly speaking, in the context of the P power exam, the scalar versus vector control that they've mentioned in the reference handbook, that applies to the DC AC drives. Okay. So I'll repeat my question. This 6 pulse versus 12 pulse business, does this apply on the AC to DC side or the DC to AC side? Is it during the rectification phase? So take a look at it here, guys, or elsewhere. It is during the rectification phase, correct? So when we have a 6 pulse converter for a 3-phase system, if we do full wave rectification, so let's say I have a phase A, then I have a phase B, right? And then I have a phase C. These sketches are not that great. So when I do a full wave rectification, I have a positive pulse, a negative, a positive, a negative, right? So from phase A, let's say, if I do a full wave rectification, I'm going to get 2 pulses, right? For one wave cycle, for one full cycle, right? Correct? Phase B, same story. It is going to give me 2 pulses, right? And phase C is same story. It's going to give me 2 pulses. For 3-phase system, when I do a full wave rectification, I get 6 pulses. So that's this. Now for a 12 pulse rectifier, as I explained in the program as well, we have a secondary and a tertiary winding. So your transformer is also a little bit different, right? So you have a Y network, a Y connection and delta. So you have 6 pulses for here, 6 pulses for here, and that is how you generate 12 pulses. And the circuit becomes more and more complicated when we get to 18 pulses and 24 pulses and so on and so forth. Okay. So the difference is in the AC to DC conversion. Does it make sense? Okay. Now that we've answered the big question, which one is better? We are slowly but surely digging in details layer by layer. Anyone has any questions about this? Please let me know. Chris, I know this is your question, right? Originally, do you have any questions about this? Is it making sense? Okay. If you have not jumped as far as harmonics, it might be a little bit new, but when it comes to harmonics, we discuss this stuff in a lot of detail. So you sort of are getting a preview of what is to come down the road as well. Okay. Now, the interesting thing about harmonics is that the higher the order of the harmonics, the lower the amplitude. Because harmonics amplitude is inversely related to its order. Okay, what is the order of harmonics? What is amplitude? Amplitude we know, obviously. Let's say if this contains multiple harmonics, right? The height, okay, is basically the amplitude. Now, what I'm saying over here is that the fundamental is 60 hertz, right? So if I have a third order harmonic, which is 180 hertz, this third order harmonic, let me just quickly sketch this. Let's say this is the amplitude of a third order harmonic. Now, if I have an 11th order harmonic, okay, which will be 60 multiplied by 11, that is going to be 660, okay, hertz, correct? First of all, the frequency is going to be like this, okay? The order is basically the multiple of the fundamental. The more important thing to remember is that the amplitude of higher order harmonics is much, much less as compared to that of the lower order harmonics. Now, why does it make any difference? Makes a lot of difference because the dent, the impact that a higher order harmonics makes to your fundamental is much less than a lower order harmonic because of the amplitude. Okay. Does it make sense? All right. That's why we don't really worry about high order harmonics. We are more obsessed with lower order harmonics. So where is this going? The fact of the matter is that when there's an equation, right? And it's not given in the reference handbook, but it is something that we need to understand that the characteristic harmonic, you can say the more dominant harmonic in this type of a circuit can be determined by this equation, which is n times p plus minus 1. What is n and what is p? N is the number of integers, so you can increase that 1, 2, 3, 4, 5, 6, and so on, right? And P is the number of pulses in the rectifier circuit, okay? So if we increase the value of P, okay, if we make it higher and higher, so the base value is 6, correct? The base case, the benchmark. So if I start with 6, okay, I use this equation, which is 1 times 6 plus minus 1 gives me a 5, right? And then I keep on increasing. So 6 is fixed. I keep on increasing the value of n. 2 times 6 plus minus 1, that gives me an 11, right? 11 and a 13, okay? So you guys get an idea that when I'm using a 6 pulse harmonics, I'll get started with as low as a 5th order and a 7th order, plus minus, right? And then I will get a 11th order and a 13th order. Now let's say instead of 6 pulses, I decide to use 12 pulses, right? Using the same formula over here. So if I use 12 pulses and the first integer is always going to start with 1, so I have 12 plus minus 1. So what am I starting with? I am starting out with a value of 11 and a 13 as the first set of harmonics, characteristic harmonics, that a 12 pulse system is going to offer. Does it make sense? So this is a higher order harmonic as compared to 5 and 7, which are lower order harmonics. And the lower order harmonics dent our power quality much more than higher order harmonics. Okay, that is a primary reason why we prefer 12 pulse, 18 pulse, 24 pulse where possible over a 6 pulse system. Does it make sense? Okay. Now, if you want to do a side-by-side comparison, we can be a little bit more sophisticated further. So you see, we started with a yes-no answer, right? 12 or 6. And then we are making use of the tools, the knowledge, the concepts that we've learned and systematically applying it to our question. Okay. All right. If you want to do a side-by-side comparison, harmonic distortion, you can see significant generation of 5th and 7th. This is all based on this equation. Unfortunately, the equation is not given, right? And similarly, the discussion around 6 pulse, 12 pulse, 18 pulse is not given in the reference handbook, at least directly. Okay, but the reason I included this question in today's discussion is because I think that this is a very good question by the student. Okay. So harmonic distortion is low because we don't have, the lower order harmonics, right? And there's also phase shifting configuration, and we can go in that detail, but I don't think that's necessary. If you just make use of this equation, this will be decent enough, good enough for you to understand why it does not include lower order harmonics. Obviously, the power quality is much better with the 12 pulse, right? The cost is the only con. So the question was, what are the pros and cons of 12 pulse? I would say everything is a pro in terms of benefits, advantage, that you have better power quality, lower harmonic distortion, all the good stuff. The disadvantage is the fact that you have to fork out a lot more money. And then even this transformer, surprisingly, I should mention this. I've actually worked on projects where we have implemented 6 pulse versus 12 pulse, right? It's not always depending on the size, the configuration, it is not always the actual VFD that is expensive, right? In order to make use of this VFD that offers 12 pulse conversion, you actually have to have a dual winding transformer, right? You have to have a secondary and a tertiary. The cost of this transformer itself can be a big element. All right. So you have to have additional components, and then obviously more labor, more material cost, and whatnot. Complexity. So this is an advantage. This is simpler. This is more complex. Efficiency. So you have higher efficiency. All the qualitative stuff is going to be much better. Physical size, smaller footprint, because You can use it for space constrained areas. You don't need, dual windings. You just need a simpler transformer, and even the controls and the footprint of the actual VFD is going to be much, much smaller. So large size is required. Availability, you almost always have to order them in advance, and they will have a lead time. Compare this with the 6-pulse drive, where you don't have to worry about it as much. I don't want to say that they're off-shelf items, maybe for the smaller ones. Typically on different projects, we've always had to order them as well, and they would have a lead time. So they're not ready-made, but they are much faster to procure as compared to the 12-pulse drive. Okay. Now, again, guys, the reason I included this problem is to give you an idea that these type of open-ended, knowledge-based questions, which the reference handbook is not going to help you out with. There's no particular knowledge piece, right, that can be directly used to answer this question. You can see how this question, while answering this question, we basically built upon different nuggets of knowledge, right? And are able to sort of, pack a nice punch over here. Correct? That's the key. It is the approach that I want you to be more comfortable with and synergistically connect the dots. That is the key to success on the P-Power exam. And if you want to summarize this from an examination standpoint, the first obvious fact is that the reference handbook contains limited details on VFDs. They basically have a paragraph, just a few lines, discussing scalar versus vector. And even that description, that detail, I think is just the tip of the iceberg. Because within the on-demand content, when you go through the lectures, I've basically used graphs, I've basically used equations, I've basically used the mathematical constructs in order to help you understand them. Okay. But even all of that discussion, unless you're able to go back and forth between rectifiers, then harmonics, right? And then actually the practical side of things, just going through one lecture is still not going to will not help you answer this question. So it is important to ask open-ended questions, at least during exam preparation, okay? Because it will open your mind and make you think outside the box and try to relate theory with application and practical knowledge. Not only will it help you become a better power systems engineer, but it will also, in the process, at least for your primary goal, which is to pass the P-Power exam, make you more confident in dealing with these type of problems. Okay. Any questions on this? Any follow-ups? Okay, I hope you found this helpful. And again, please go through the lecture content, on-demand content, go through all the quizzes, go through all the live training content, homework assignments, and actively go back and forth between different topics that you are studying. The beauty of the P-Power exam preparation is that it very naturally and logically builds up. Okay, there's a lot of synergy as compared to FE electrical exam where you don't have much synergy. Within sections, obviously you have, but in between sections, you don't, right? So this harmonics discussion actually shows up in section number 4 under the title of power quality. Okay, so I hope you found this helpful, and I hope that you are going to take this approach moving forward with any type of open-ended conceptual problems that you see on the exam. Question number 2. Another very interesting question. This is something that we discussed in the coursework in power quality. But what I like about this question is how the student is actually connecting VFD cables to harmonic mitigation. And if you just look at this the statement, why wouldn't VFD cables mitigate harmonics? So it tells me that the student has done his own research, right? Knows what he's talking about, all right? Because, and the way that the question is framed is actually correct. So I cannot just discount this question as saying that, you know what, you don't even know what you're talking about. VFD cables actually mitigate harmonics, right? Because the fact of the matter is, you have to look at it from the standpoint as to what is mitigation of harmonics. Okay. So does the VFD cable actually mitigate harmonic? Right. And in order to answer this question, you can say yes or no. That would be our starting point. But then to expand upon it, you will need to make use of a little bit more sophisticated reasoning. Okay. So one line question, but let me just break it down. Right. So we know that when we are using VFDs, the original equipment manufacturers, shorthand OEMs, always, especially for larger VFDs, they always recommend you to use VFD cables. Those of you who have worked as design engineers, who have actually worked in the field and maybe installed, commissioned, program VFDs, you know that VFD cables are more expensive. They are specialty cable, and the manufacturer Siemens or Eaton or ABB, whichever drive you are purchasing, they will always tell you that we need the VFD cables, or else potentially your warranty can be void. Okay. So VFD cables are a real thing. Harmonics is a real thing. They are interconnected because VFDs themselves are source of harmonics. But this term that the student used, mitigate, right? So the question is, when you install a VFD cable, does the harmonic content go down, right? We've discussed harmonics in the program. It actually is in section number 4. So are we actually mitigating the harmonics by using VFD cable? Strictly speaking, we are not, right? Strictly speaking, we are not. Example would be, an analogy that comes to my mind is, if you think about arc flash, by wearing PPE, are you mitigating arc flash? Not really, right? That's your last line of defense. And we discuss in NFP 70E in a lot more detail about the hierarchy of different types of controls, right? Mitigation would be when you are able to do substitution. Mitigation would be you install some sort of a engineering design, right? You tune up or tune down your protective device coordination. So you're actually reducing the amount or the source of the trouble. VFD cables, strictly speaking, they don't mitigate harmonics, right? In short, and again, if you don't know this, then what's going to happen is that you can go in several different directions, right? In short, they allow you to live with the problem a little bit more comfortably. Okay. Does it make sense? But the question was not simply, do VFD cables mitigate harmonics or not? The question is, why wouldn't the VFD cable mitigate harmonics? So the student knows what the answer is as far as mitigation is concerned, but is questioning or trying to understand that why is it that the VFD cables will not be able to mitigate harmonics? Does it make sense? Okay. And again, a good open-ended question. These type of open-ended questions you guys need to ask in the on-demand content. We have several, detailed mathematical explanations, derivations, phasor diagrams, circuits, graphs. And when you have a good handle on them, and even in the live training with the homework assignment content, the next stage for you is to be able to deal with these open-ended questions. Okay. So this is how I approached it in a stepwise manner. Let's go back to the basics. What are harmonics? Okay, very briefly, they are generated within power electronic devices like VFDs, UPSs. Okay, when we are doing switching, the more rapid switching we are doing, the more harmonics are basically created, and a plethora of harmonics are created. Okay, now you might argue that, okay, let's not do switching if it is so harmful. But if you don't do switching, you are not going to have chopper circuits. You won't have buck boost converters, right? You won't be able to do the AC to DC conversion. So switching is required. We cannot eliminate that. Otherwise, our power electronics devices are not going to be able to do the magic that they do, that we rely upon. Okay. So what is the source of the problem? What is the source of harmonics? It's switching. And switching is inevitable because we have UPSs, we have VFDs, we have a lot of other electronic devices, right? For which it is very, very important. So that's our starting point. Step number 2. What is the role of VFD cables? Now, this basically unlocks the problem for us. If we look at VFD cable versus power cables, right? Where is the difference? So standard power cable, let's say you decide that, okay, for this ABB VFD or Siemens VFD that I purchased, I'm not going to use the costly VFD cable. I'm going to stick with the regular power cable. The issue is that the regular power cables are not designed to handle high frequency switching caused by VFD. So what allows the VFD cables to handle high frequency switching? They're constructed with additional stuff. What is that additional stuff? So you have basically shielding, you have additional insulation. The construction is symmetrical in order to mitigate the electromagnetic interference. Okay, they have a sheet right on top of them to sort of to carry the noise signal, and the insulation is much more heavier duty. So what you are doing is, let's say it is winter, right? It is snowing outside. You are not in control or have the ability to basically turn a switch off to let it to basically stop the snow, right? Or the cold weather and turn it into a blue sky, right? But what you do is that when you step outside, you add layers of jackets, right? Multiple layers, right? Like a muffler and, um, gloves and boots that can help you still stay warm when the reality outside is not changing. That's what the VFD cables are doing. It's not helping you stop the snow, but at the same time, it is going to make sure that you don't get pneumonia, right? You don't get cold. Does it make sense? Okay. So why do we use the VFD cables? Again, as I mentioned, reduction in EMI, electromagnetic interference. So these features such as shielding, robust insulation, they are going to help contain and reduce the EMI, electromagnetic interference, which are generated by the harmonics by the high frequency switching. Improve power quality. So when the electromagnetic interference is reduced, okay, because of their construction, because of the fact that they're able to conduct some of the noise signals on the sheet, right? They will be able to maintain a better power quality overall as compared to your power cable, which will be more highly stressed. Okay. Now, the final reason why we want to use the VFD cable, and in a lot of cases, I've been on multiple projects where ultimately it is the OEM requirement. It all comes down to, okay, you're purchasing this VFD, which is $100,000, correct? And if you want to keep the warranty for 5 years, 3 years, or whatever the timeline is, we want you to purchase the specialty VFD cables. And multiple stories on this, but typically what I find is that when you are doing estimation for different projects, okay, and the layout of the equipment, I'm digressing a little bit, but hopefully it will be helpful. The layout of the equipment is not fixed by mechanical engineers. Okay, you know that there are going to be X number of motors, and of those motors, let's say 50% of the motors are going to require VFD. So you know that, let's say you have 5 motors that are going to require VFD. Okay. Now, what ends up happening is that in your electrical budget, depending on how you basically do budgeting and whatnot, what is norm, you account for 5 VFDs, right? And you have sort of an estimate of where this equipment is going to be located. I have seen scenarios where, because of whatever reason, they end up putting motors at very far distances. Okay. Let's say you assume that the motors were going to be pretty close by, right? But they end up being at a very large distance. Now, how does this impact you? It impacts you because these cables are very expensive. So much so that your cost of the VFD cabling can become equal to or sometimes even exceed depending on how bad this scenario is, even more than the cost of the VFD, right? And the project manager is then going to be breathing down your neck. Be like, what is this? Why do I have to step into my contingency fund and accommodate something that is not accounted for? And in your defense, you're like, okay, in the initial phase of the project, we didn't even know. The best that I was told was that they're going to be X number of motors, and the layout was all floating, right? We didn't know where these motors are going to be placed. So a conservative estimate was, let's say, 100 feet of cable, right? But when the layout got frozen and fixed and other aspects of the project were fine-tuned and defined, now each one of these cables is actually 300 feet long, right? And the time that is going to be required to procure these cables, the amount of money that is going to be required to get these multiple reels and then storage and everything is going to basically accumulate. Okay, so you got to be really careful with this. And at the end of the day, if the PM is like, okay, use the regular cables, is there a cheaper alternative available? Then the OEM kicks in, right? Your vendor, ABB or Siemens or whoever you're purchasing the drives from. And they'd be like, no, if you use ordinary cable, we will consider it as a violation of our warranty requirements. And you then whether the VFD fails the very next day when you switch it on, or it lasts you 10 years, right? We cannot take any guarantees. Does it make sense? So practically speaking, this VFD cable business, it is crucial, right? Now, when you understand what is the reason why they are important, why they are used, okay, and that is just an extension of, from an examination standpoint, that's just an extension of your understanding of VFDs and harmonics, okay? So very nice open-ended question, and hopefully you find this helpful as to how you should systematically approach these type of problems. And if you want to learn more about preparation of FE Electrical and Computer exam and the P-Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.